The topic that I am going to talk about is on sensors and image formation. The sensors that we are going to talk about are image sensors. All right, image sensors, we know a wide variety of image sensors, like they may be one dimensional, like all scanners or photocopy machines. They are all one dimensional sensors, wherein there is a sensing plate that goes up and down. There are two dimensional sensors, which are our ordinary cameras, right, and three dimensional sensors, for instance, to range imaging devices. Okay, we are going to talk about some basic things. So, I will start off with that, basically a little roadmap of today's talk. First, I will be delving into images, little bit about images themselves, then give a little introduction to image sensors, what I would mean by image sensors. Then we will discuss two parts. One is what I like to call the physics of image formation, and the other is the maths of image formation. By physics, I mean that if there is a particular point in the world with a particular color or a particular intensity level, अगर उसको image किया जाए, once we image that, what will be the color or the intensity level at an image point. All right, that is something that I refer to as the physics of image formation. Maths of image formation, by that I refer to the fact that if I have a point in 3D x, y, z, image में ये कहाँ पे आएगा, where will the corresponding image point lie. All right, first is what will be the color or the intensity at that image point, that is what I refer to as the physics of image formation, and the maths of image formation would be where would it lie. And then finally, new sensors. What are disadvantages of existing sensors? Why do we need new sensors? Well, some of this is textbook level material. I have I'll give a couple of pointers to references, and quite a lot of it is 90s development. So, you will not find this in textbooks very easily, all right, generally taken from papers. But the other interesting things are the following. Papers से तो लिए गए हैं, but they are actually conceptually pretty simple, and coming to think of it, some of the most profound results in research actually come from very simple ideas. This bears testimony to that. Okay, the three books which I am referring to are, well, this is just about the Bible of image processing. ये तो हर एक के पास ही शायद होगा. Gonzalez and Woods. Then there is a book on RoboVision by BKP Horn. This is a pretty old book, but it's pretty nice. And then there is a more recent text by Fauchera. Well, you can basically pick up any book on image processing and get just about the basics here. So, let us start with images. What do we mean by images, and how do we relate to that? Now, the basic idea here is the following. Now, just as you have a signal, so sampling is something that everybody would be familiar with. So, essentially the idea is there is an independent variable and there is a dependent variable, all right. So, जो dependent variable है, let's imagine that you have your independent variable on the x axis and the dependent variable on the y axis, right. If you quantize both, that is how you get the discrete domain or the digital domain. Essentially अगर आपने time में quantize किया उसको, you have a discrete signal, और अगर उसके values को भी quantize किया और let's say binary number से represent किया, then what you have is a digital signal in that sense. So, you can generalize this to two dimensions. If your sampling is along two axes here, if your independent axes, just like in an audio signal your independent variable is time, right. In this case your independent variable is space. You have sampled a signal across space x and y. So, x and y are the variables, or the height can be taken as a value at that sampling point, something like this. I could have an alternate representation in terms of a matrix, right. Every sampling point is a box, all right, like this is coordinate 0, 0, and here I have represented the height as being proportional to the brightness. इधर सारे एरिया में height 0 है, so that I have represented by black, और यहाँ पे height 255 है, 255 है, तो that I have represented by white. All right, so this is just about what an image is, and in fact the little sukti ekam sad vipra bahudha vadante, it's pretty applicable here. एक ही सत्य को बुद्धिमान लोग अनेक तरीकों से देखते हैं. One truth is interpreted by the wise in many different ways. That's exactly it, and that is exactly why image processing is something that should be of interest to a lot of people. Image processing, because it has algorithms, should be of interest to people in computer science. Image processing, because it involves two-dimensional signals, should be of interest to people in electrical engineering, signal processing. फिर इसमें robotics applications हैं, so people in control theory would be interested in it. Then nowadays we are talking about transmission of images across networks, so people in networks should be interested in it. It's basically a multidisciplinary subject. And of course, one of the areas that madam is interested in, medical imaging, that in the US for example, that is the main source of funding for most image processing project. So this is just about images. What about video? Now okay, ये तो हुआ है gray level image. Now if I can talk in terms of an image in terms of three planes, just as it is for color TV transmission, if I can talk about a red plane, a green plane and a blue plane, each of them individual grayscale images but interpreted as different planes, that has a color connotation. So this is exactly what a color image is. So what is a video? Video mein basically there is another axis which is the temporal axis. There is a third axis or a temporal axis, that is frames of video taken across time. So that is video. So this was just an introduction. Alright, where are image sensors used? And essentially this is what I was talking about. In our 6th standard, most of us have studied this in physics. So this is all about imaging. In fact, most of imaging in any band of the electromagnetic spectrum can be taken as composed of a lens or a pinhole model and perspective projection. Okay, this is what I explained before. Physics matlab what is formed at a particular location in an image. Agar color ya grayscale value intensity world point में इतना है, image point में क्या रहेगा. So that is what I refer to as the physics of image formation. This is non-standard terminology. And the mathematics is where in the image is it formed. If I have a point x, y, z in the world, where in the image is it imaged to? Alright, because there is a loss of dimensionality, of course, right. From a 3D space we are going to a 2D space. Alright, first I will come to the problem of the physics of image formation. Well, there are these two terms that most of us are familiar with. We would have studied this in school also in physics. There are two terms that sound similar. One is radiance, the other is irradiance. Alright. Now radiance is defined as the differential power divided by a small amount of unit area and a small solid angle. Alright. So this is the power per unit area over which it is radiated, per unit solid angle into which it is radiated. And on the other hand, irradiance is defined as the differential power per unit area. Okay. Now the difference is as follows: irradiance अंदर आ रहा है, radiance बाहर जा रहा है. Okay. And essentially what we want to find out is the relation between the radiance at a point on the object and the irradiance of a corresponding point in the image. Okay. Radiance and irradiance, that is the way physicists define it, but how does one remember what they are? Okay. So radiance, it is just like money, right. When it is coming in, we are not worried about kahan se andar aa raha hai, but when it is going out, radiance, we are definitely worried about the direction where it is going about. Okay. So that is one easy way to remember what the difference between radiance and irradiance is. Radiance is always per unit solid angle into which the energy is emitted. So essentially the physics of image formation is the relation between radiance at a point on the object. This is what I talked about, radiance or in a way intensity of a 3D point और image में वो कैसे form हो रहा है. That is it. Okay. Yeah, these are just the definitions. So this is how we define solid angle. Since there is a bit of math here, I will just skim through it, but just get the basic idea through. Okay. So theta, if theta is the angle of incidence on a particular surface of area A, then okay, this is a planar surface of area A, then we define a solid angle as the effective area or the foreshortened area. We are all familiar with foreshortened area, right? अगर एक टॉर्च लाइट को एक कागज़ के सामने ऐसे पकड़ते हैं, there will be a lot of intensity there. लेकिन अगर foreshortened area ज़्यादा हो गया इस सेंस में, if the angle is more, then the intensity spreads out, it reduces. We are all familiar with this, right? And essentially what we are trying to derive here is the fourth power cosine law. All of us have studied this in physics, possibly first year. Okay, this is the way we define it, and of course, the solid angle is also inversely proportional to the distance from the small patch. यहाँ पे जो radiance है, how do I relate this, or rather in other words the brightness of this object patch with the brightness in this image patch. All right, this is what we want to do. This is a lens which has diameter d. This is a parameter called f, often equated to the focal length if it is a thin lens model, and this is the distance of the lens from the object. So, the basic idea is that the solid angle of the cone of the rays, the solid angle that is formed here, ये जो solid angle है, that should be equal to the solid angle here, right? That is geometry. If you take that in a plane, it is basically saying that the two planar angles should be the same. All right, if you take a cross section, this is perfectly fine. The other thing that we will basically assume two physical results. ये तो एक है. The other thing that we will assume is that if I have whatever is the amount of radiation that is emitted into the lens, the same amount comes out. Okay. This is not like a government official who will absorb some of the money that is coming in and throw out less, but we are assuming कि absorbing यहाँ कुछ नहीं हो रहा है. Okay. I hope you will be absorbing what I will be saying, okay, not in that sense, right. Okay. And in an image we basically find out these relations. We find out the effective area, okay, that is perpendicular to the rays. The distance from the center of the lens would be essentially this, f divided by cosine alpha. Now, why is it divided by? Because cosine is base by the hypotenuse. So, essentially it will be what we are trying to find is this particular line. So, if we relate this through the distance here, then what we are doing is we need a divided by cosine relationship. So, we can compute the solid angle that is subtended here. We have a similar relationship for the object, right, and we get two expressions for the solid angle. So, we have two expressions for the solid angle, we can equate them, all right, and of course, we remember our basic relationship. So, from the radiance we can get the power as follows, radiance ke relationship se. So, we have a small amount of power here, delta p. We can put in the value that we got here in our previous derivation, just put in this value and then use the fact that no power is lost. The energy that is incident is also emitted by the lens. So, at the end of it, the bottom line here is this. This is better known as the fourth power cosine law. Okay. This basically is a relationship between the radiance of a 3D world point and the irradiance that is there in the image. All right. This is what we tried to derive, and I have just kept this part out. Okay. Now, we will talk about the math of image formation. Now, in the math of image formation, well, there is a little bit of math here. So, maybe I will come to it after some time. All right. Let us get to some better things. The math of image formation, essentially what we are trying to do is we are effectively trying to model perspective projection, that is all, because that is the very basic entity of image formation for any region of the electromagnetic spectrum, and it is this that is the basic science behind a camera. Perspective projection, I think every one of us is familiar with, right. So, I will come to this part a bit later. All right, maybe I will draw a little diagram here. Well, most of us are teachers, right, and having a blackboard nearby is something that one sometimes irresistible, right. Most of us teachers tend to gravitate towards blackboards the moment we see them. Essentially, the idea of perspective projection is as follows. If one has a point in the world, right, if this is of height x, yeah, maybe I should move a bit more, and if this is this amount, then we have basically just by using similar triangles, we have a neat relationship, right. Small x by f is capital X by z. We know this from similar triangles. This is essentially what we are trying to do. but there will be something more to it which I will come to. Okay. These will be some mathematics which I will come to a bit later. Now, what we are trying to do is the following. Now, we know the basics of image formation. We basically know how an image is formed. One of the things that we try to do now is to basically understand what is it that limits today's image sensors, and using today's image sensors, how can we get something more out of them. All right. Why do we consider projective images? Because it comes naturally, right. That is the way lenses are built, and mathematically it gives a common framework for all transformations. This part I will come to a bit later, because this involves a bit of math, but first let me motivate the problem at hand. Okay. Because essentially I can describe a camera by this matrix. This is a projection matrix. If I have a 3D world point and I have a 2D point in an image, so this camera projection matrix basically governs the process of imaging. We have a loss of dimensionality, right. So, this is what governs it, and camera parameters are basically of two types. One of them is a set of internal camera parameters, which as the name indicates camera ke andar hai, essentially things like the focal length, right. That is an internal property of the camera, and sometimes the focal lengths of the x and y directions are slightly different. This is something that is called an aspect ratio. Okay. People in graphics or imaging would definitely know what an aspect ratio is, and there might be a skew. So, there is one parameter to account for skew as well, and of course, then there is the of the principal point, right. That is exactly where the principal axis cuts the image plane, and of course, we have the external parameters, which is a Euclidean transform, essentially 3 rotation angles and 3 translations. Okay. So, this is about a perspective projection model, and this is a common model of perspective projection. So, now let us come to what are some limitations of existing sensors and how can we overcome them using our off the shelf cameras and some simple algorithms. All right, हम सेंसर को ज़्यादा बदलेंगे नहीं, कैमरा को वैसे का वैसे ही रहने देंगे, but we will apply some algorithms and then get something more out of it. What we are talking about is there are some disadvantages of existing sensors. All right, there are some disadvantages of existing sensors due to which we would like to go in for new ones. Suppose काफ़ी सालों बाद there is a gathering of friends, okay? काफ़ी लोग एक जगह पे हैं, all right, और सबका तस्वीर खींचना चाहते हैं, तो क्या बताएंगे, क्या उनको बताएंगे? We'll ask them to stand more or less in a line, or why? Because every camera has a very limited range within which things get perfectly focused. All of us have experienced this, right? So, a camera has a very limited depth of view in that sense. Okay? Ideally we would like to have an image wherein everything is equally focused, right. Typically in these Saas Bahu serials, what do we see here? Bahu standing in front, suddenly the camera focuses behind where the Saas is standing, right. See, these sort of cinematographic effects come out pretty well there, because every camera has a range, distance range within which objects would be focused. But how nice would it be if every pixel in the image were equally focused, all right, because our eyes can do a lot of things which cameras cannot, right. Dynamic focusing, for example, okay, it is very difficult for cameras to get that sort of thing, but however, how nice would it be if I have a camera which can take images जिसमें कि हर pixel focused हो. I will show a couple of examples. Another problem, okay, suppose you have the same gathering of friends, all right, and let us suppose you have a large number of friends. Okay. So, if you ask them to stand in a line, one problem is, as a photographer I would have to go behind, है ना, because every camera has a very limited field of view in that sense, right. If I want a larger field of view I would have to go behind, but I would lose in terms of resolution, all right, resolution इतना अच्छा नहीं आएगा, although I will get a field of view, but I will not get that amount of resolution. So, how nice would it be? Let us make a wish list. First, we want a camera in which in the images every pixel is crisply focused. Second, we want a camera wherein I have a wider field of view. All right, I have a wider field of view. Ideally, I would like to take a camera. Let us say there is this gathering of people, or maybe our 2 engineers who are recording this today. Ideally, for them it would be nice if they could simply take shots of the crowd and then somehow stitch them together. Okay? That would be nice, because each individual image would retain the same resolution, and at the same time the stitched image overall the size would be larger at the same resolution. Okay? That would be something nice. Then improving the resolution. We have a very friendly country to our western side, right, and suppose there is a spy satellite or a spy aircraft that is flying overhead, and let us say we want details of a particular point in the image, zyada details chahiye. So, that is the problem of super resolution. We want an image at a greater resolution than what we have. I will show a couple of examples of that. And lastly, it would be nice, see, every camera has a very limited field of view. It would be very nice if a camera could look all around. We are all teachers, right? क्लास में ये तो बहुत काम आएगा, आगे पीछे ऊपर नीचे अगर हर जगह simultaneously एक ही टाइम पे in real time if it can see. This is the idea of an omnidirectional camera. Now, these are some of the developments of the 90s that I would like to show along with a couple of examples. Yeah, this is the reason why we go in for more sensors. Ye dil mange more. So, these are the 4 things that I am going to talk about today. One is super resolution, that is getting images at a higher resolution than the original one. Then mosaics, that is stitching together images. Nowadays, we have these digital cameras that come in with a panorama mode. Have you seen this? वो कहते हैं कि हाथ में रखिए इसको और फिर धीरे से घुमाइए उसको, धीरे से घुमाइए, and automatically it will try to stitch the images all around into one and give you a combined image. Okay, that is one example of mosaics. Then there is an omnicam, that is an omnidirectional camera, a camera which has a 360-degree field of view, amazing, चारों ओर देख सकता है ये. And finally, we have something called a non-frontal imaging camera, which has every pixel equally focused. It's pretty interesting. Let us come to the first one, super resolution. This is an original image of a shoe, all right, of all things. Now, if I want an image of double the size, all right, what is one's natural tendency? क्या कर सकते हैं? We can say that जो 1 पिक्सल है उसकी जगह 4 पिक्सल्स लगा दें, right? That's duplication, pixel duplication, or in terms of signal processing this is called zero order hold, all right. Now, what will happen if I replace every pixel by 4 pixels? Size तो बड़ा हो जाएगा. What might be a disadvantage? Resolution, exactly, because of something called, what people in signal processing want to avoid at all stages, called aliasing, all right. So, or the other thing which everybody has seen is a boxy sort of effect in images, blocky effect आ जाता है, right. So, to remove the blocky effect, one of the things that might have been done as a part of this short term course is a low pass filter, right, smoothing. You can do a low pass filtering operation, but then with a low pass filtering operation जहाँ पे sharp features थे वो भी smooth out हो रहे हैं. So, that is not something nice. So, what we would want to do is get a super resolved version of the image. Okay, so, this as such is a hardcore signal processing problem and a very difficult problem, that too. So, this is an original image, this is an image with bilinear interpolation, all right, simple bilinear interpolation. This is a super resolved image. Okay. Now, note that you can see the details of the stitches now. Okay, I'll just explain the signal processing problem also, just give a brief introduction to it. I'll just explain a bit of the theory here. Okay. So, a little bit of the theory is as follows. See, the problem of super resolution, since most people here are electrical engineers, well, I'll generalize this, electrical, electronics and whatever. The problem is as follows. If I have a particular signal, okay, samples of the signal, let us say I have something like this, Now, what I want to do is I want to get something at ominous. Can you hear me? No. Okay. All right. So, what I am trying to do here is I am trying to double the number of sampling points. All right. 1, 2, 3, 4, 5. Okay, maybe I will do it from this side. Would that be more comfortable for the recording engineers? ये बेहतर है या वो बेहतर है? दोनों ठीक है. Okay, that's nice. So we don't have a digital world, right? It's not on and off. Okay, so what one wants to do is one takes these. So essentially, one wants a signal at double the resolution. All right. This is essentially what wants. Double the resolution means double the number of sampling points, but we want to find out what is happening here at these intermediate points. All right. Now, one method is pixel duplication, which is also called by people in communication as a zero order hold. So essentially what one is doing is यहाँ पे जो value है, one is duplicating that. So fine, one has another image that is at double the resolution, okay, but there is no new information at these sampling points. At these sampling points there is no new information, right. So alternatives क्या है? What are, can you suggest some alternatives in which I can get more information? Interpolation, exactly. One interpolation is simple linear interpolation, यानी ये दो original sampling points हैं, I can join them by a line and जो intermediate sample है उसको I can extend it to meet it here. All right. Similarly here, I can do this. Similarly, I can do something here. But again, wait a sec. Again, we are not giving any new information. All right. It is just as if one has low pass filtered it. कोई नया information नहीं है. All right. So whether or not I do a zero order hold or a first order hold, I am not getting any new information out of it. So damn it, how do I get more information out of it? What is the basic problem here? The basic problem is that of estimation. All right. We want to estimate the original signal, which could be something like this. See, this is the basic problem. This could be my original signal. All right. And because if I blow this up here, so essentially I will have something like this, something going here and so on. What I want is the value at the intermediate point. So do you realize the problem? So in terms of signal processing, what is it that is lost? It is the high frequency components of the original signal जो गायब हो गए हैं in the process of sampling. So therefore the process of super resolution is one of estimating these high frequency components by some method, and this also tells you that the problem is very difficult. Why? Because given two sample points, उसके बीच में क्या है? There are an infinite number of solutions. So typically what one does is one puts it into a constrained optimization framework, Lagrange multipliers, right? One puts in constraints such as the overall image should be smooth. If there are points of discontinuity, they should be explicit. So one typically models this using Markov random fields, okay, and associated Markovian models, and tries to solve for that. Okay, this is the basic problem of super resolution. And another reason for looking at these are, well, they are very recent developments, and the second point is Indians have been associated with all four of them. For instance, for super resolution, the one gentleman who has two textbooks in the field, these are the only two textbooks in the field, is an Indian and is a ex senior colleague of mine at IIT Bombay, Professor Subhashish Chaudhary. In fact, I just stole these images from one of his presentations. Okay. Mosaics. This is the second problem that we will look at. In mosaics, the idea is, well, that is ideal, right? I take my camera here, 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 I take a couple of images and stitch them together. That is the idea. So, the idea in mosaics is to increase the field of view without increasing the cost, all right. That is the idea, and general mosaicing is an unsolved problem. Why? I will just come to it. And easy solutions exist only for special cases like satellite image mosaicing. ये तो देखा होगा, Google Earth, most of those images, okay, are basically taken at different points in time from a satellite, that is at a, or from aircraft, high flying aircraft, जो कि बहुत दूर हैं from the earth's surface. So therefore the approximation, that of orthographic projection, is pretty valid. All of us who have done engineering drawing know what orthographic projection is, right? Z coordinate को हटा दिया, you get a 2-dimensional entity, or worst comes to worst, scale कर दो, up or down, okay. And that orthographic assumption is valid in such cases where the distance between the object and the imaging point is very large, okay. No perspective effects come into play. There are, see, if you look at Google Earth images or Google Maps or Yahoo Maps, if you take the satellite ones, you will sometimes notice some discrepancies, okay. Maybe we will come to that at some point in time. And yeah, this is satellite image mosaicing, then mosaicing images of a blackboard. These are solved problems. However, the general problem of mosaicing is unsolved. And अभी तो engineering drawing का जिक्र हुआ था. I can relate that to a problem in engineering drawing. हम में से कितने लोगों ने sheets copy किए हैं engineering drawing के course में? Let's all raise our hands. I have also done it, okay. If you have done it, how would you have done it? कैसे किया होगा? In India, this is popularly known as GT, exactly. You place an optically true slab of glass, you have a monochromatic light source underneath, and then you basically take a projection and imaging. But you might say कि उसमें तो उतना ज़्यादा credit नहीं है, क्योंकि हूबहू बगैर सोचे समझे दूसरा sheet बन जाता है. Suppose you were to do it nicely. Suppose you wanted to try it out on your own also, and also just wanted a check कि सही तो हुआ है. One of the things you could do is you could take one of those sheets, go to a photocopying machine, right, but then suddenly discover कि कोई sheet उतना बड़ा तो नहीं होगा, cartridge paper उस size का. So how would you do it? You would do it in stages. थोड़ा सा part photocopy machine में दिया, उसका निकाला, थोड़ा shift किया उसको, put the other part under the photocopying machine, take that, and at the end of it stitch them together, right. Take a pair of scissors, a tube of glue, and stitch them together. How many of you have done this? I have. And any of you who have done this would also realize an associated problem. Alignment होता नहीं है. Why? If you understand that, you will understand the fact that general mosaicing is an unsolved problem. क्या होता है? Angular shift को account कर सकते हैं, because any of those small A4 sheets we can rotate, we can translate and rotate. These are essentially 2D Euclidean transforms. वो कर सकते हैं, ठीक है. दूसरी sheet को थोड़ा सा घुमा के लगा दिया. That can be accounted for. लेकिन फिर भी perfect alignment क्यों नहीं होता? Can you suggest a reason? If you can, you have understood why mosaicing is not possible in the general case. See, typically paper tends to get dog-eared, right? थोड़ा मुड़ जाता है paper, और जिस वक्त मुड़ जाता है, you cannot, there is a 3D effect. जैसे किताबें जब photocopy करते हैं, but you would have seen किताबें photocopy कराते वक्त बीच का जो portion होता है वो कैसा आता है? ऐसा आता है, it comes distorted. Why? There is a 3D effect. It's not a perfect 2D effect. All right. So it's very difficult to align a sheet in a photocopy machine in such a way that you have a perfect 2D to 2D copy. That is exactly the point that you are trying to make. That is exactly it. So unless you solve for the 3D problem, unless you solve for the problem of finding 3D structure, you cannot, without knowing the 3D structure, you cannot do general mosaicing at all. Okay, that was a little bit of an introduction. Now for a case where it's possible to do mosaicing. Okay, this is something that's called a homography. I'll come to some mathematical details. I'll just give an application and then I'll do a bit of the math. This is essentially what, essentially it can be mathematically proved that, suppose I have images of the blackboard. Incidentally, when I teach this in class, what I do is I take a camera to class and shoot everybody, okay, with a camera of course. The idea is that I take a camera at a point where the camera cannot see the complete blackboard, all right. I take it relatively close and then I take different images of the blackboard with that camera and then get people to stitch it together. This problem is defined, this problem is solvable because corresponding points in any two images are related by a 3 cross 3 non-singular matrix called a homography. All right, this is a very neat result. It is simple but neat result. All right, and one of the techniques here is some gory mathematical details here. So, quickly run through that is to minimize the sum of squared errors between the overlapping regions, essentially the pixel values. Okay, you want a solution that would minimize this overall sum of squared errors. It is an RMS method, right. I will come to that. I will explain this with the help of an example here. All right. And of course, mosaicing would involve three things. First is image alignment. Remember that photocopying problem. A4 sheets हैं, you would like to align the sheets. Next is cut and paste, overlapping regions में एक में से काट देते हैं, दूसरे में paste कर देते हैं. And last is blending. Okay, कई बार एक photocopy थोड़ा light आता है, थोड़ा dark आता है दूसरा वाला. How does one get through them? All right. That is called image blending. So, mosaicing involves all three of these. I will first go through a couple of examples, lots of math here. So, I will directly come to an example, the math I will do on the board. Okay, you have an example here. Okay, this is where I was trying to teach image mosaicing. So, I was just giving an example of an aircraft that's flying over, let us say this is a river and couple of vegetated regions here, there is a bridge. एक image aircraft ने यहाँ पे लिया है, दूसरा image यहाँ पे लिया है, and I have shown these two images out here. Okay, and I am trying to teach mosaicing. So, here basically I have written things like alignment, cut and paste and this. Of course, you can't see much because it is my horrible handwriting. Okay, what I did was I took arbitrary images of the blackboard. I did not have a planned trajectory. I took arbitrary images of the blackboard. Okay, I walked all around the room. कभी कैमरा को थोड़ा ऊपर लिया, कभी थोड़ा नीचे लिया, इधर लिया, उधर लिया. I have taken arbitrary images of the blackboard as you can see here. Okay. And so, what do I do when I have these arbitrary images of the blackboard and I want to stitch them together? We are all teachers, right? We give out assignments. That is exactly what I did. I gave out a class assignment and this is one example of stitching them together to get one complete mosaic. All right. Couple of things that you can notice here. This is obviously not perfect, right? Why is this not perfect? Which of those three things are not really satisfied here? Image alignment, cut and paste, blending. Blending is not really satisfied here, and alignment also, right? Because as you can see, every pair of images is more or less aligned, but the alignment tends to get a bit off as you take more and more. All right, errors tend to propagate. Okay, I will talk about this also. See, this was done at a pixel level. Nowadays, you can do things at a sub-pixel level also. Basically, you try to fit a surface to an image and then essentially put a parametric form onto it, get a functional form and then try to find out exact coordinates. So, with sub-pixel level accuracy, you can get some rather well aligned images. The other thing, okay, so that this would still come out as a straight line. अच्छा, अब बात रही blending की. Can you suggest techniques to blend images? और problem है आता कहाँ से है? This is actually a feature of modern day cameras which is actually bad from the point of view of image mosaicing. बताइए, any guesses? Yeah, light effects, madam, और बताइए. All right, I'll give the answer. It's something called automatic gain control. हर कैमरा में, most cameras come with automatic gain control. In fact, with very costly cameras, you can disable automatic gain control. The idea is the following, कि अगर आपने देखा होगा जनरली विद डिजिटल कैमरास, अगर आप डिजिटल कैमरा को किसी अंधेरे जगह पे लेके जाएं और इमेज लें, यू विल नोटिस दैट इट गिव्स एन ऑटोमेटिक गेन टू द एंटायर सीन और इमेज आ जाता है, राइट और अगर बहुत ब्राइट जगह पे लेके जाएं, थोड़ी देर में यू विल फाइंड दैट थिंग्स आर गेटिंग डार्क एंड शार्प. लेट्स से यू टेक इट टू अ ब्राइट सनलिट एरिया, थोड़ी देर बाद यू विल सी दैट द एंटायर थिंग डजंट सैचुरेट, थोड़े फीचर्स दिखने लग जाते हैं. सो द कैमरा ऑटोमेटिकली एड्स अ गेन फैक्टर. ओके, so this is the scaling point that I was talking about. Cameras do it automatically, but nowadays there are cameras wherein you can disable automatic gain control. आप disable कर सकते हैं इसको ताकि one uniform object more or less overall appears as the same brightness, because otherwise see this part of the wall and something that is a couple of millimeters close by should not vary that much in intensity. So can you suggest some methods for blending? अगर automatic gain control को हटा नहीं पाए क्या करेंगे? हाँ जी, एवरेजिंग कर सकते हैं. दैट्स एग्जैक्टली इट. एवरेजिंग इज बेसिकली लो पास फिल्टरिंग. लो पास फिल्टरिंग इज समथिंग दैट आर्टिस्ट आल्सो डू इन देयर इमेजेस. स्मजिंग, मिक्स करना, किसी कलर को मिक्स करना क्रेयॉन्स के साथ. थिंक यू वुड हैव सीन योर लिटिल किड्स डूइंग इट, राइट. पेंसिल शेडिंग, उसमें भी व्हाट वन डज इज एक्चुअली लो पास फिल्टर, स्मीयरिंग इट. यू कैन एक्चुअली डू दिस हियर. फोटोशॉप वगैरह में तो और अच्छी तरह से कर सकते हैं. एयर ब्रशिंग, पिकिंग अ कलर एंड एयर ब्रशिंग इट. There's a little problem with that. What is that little problem? Hanji? That is precisely it. Exactly. If there are any high frequency components here, if there are any sharp edges, you lose them because you have smoothed it out. Any other heuristic? Because all of these are heuristics. There is no, the answer is there is no sure shot way. Whatever suits the situation, one uses it. Yeah, interpolation. There are bilinear interpolation techniques also, but essentially it amounts to some form of smoothing. और कुछ? Median filter. So instead of a linear filter, apply a non-linear filter, like a median filter. That often helps. कई बार वो भी नहीं करता. Can you suggest any other technique? Because all of this, जैसे situation है वैसे ही कोई technique use करते हैं. Can you suggest something else? A simple DC shift. All right, take the see, if there is a RGB image, take it to some other domain, a conceptual domain such as the HSI model, right. तो जो ग्रे लेवल इमेज कॉरस्पॉन्डिंग है उसका एवरेज निकालिए. ये जो पास वाला इमेज है जिसके साथ मोज़ेक किया गया है उसका आप एवरेज ग्रे लेवल निकालिए. ट्राई टू इक्वलाइज द मीन्स एंड द वेरिएंसेस. ऑल ऑफ योर टीचर्स यू वुड हैव डन दिस. अगर कोई लैब है which are taken by which a lab course which is taken by many instructors, how do you normalize marks? You take them, you normalize it to 0 mean and unit variance, then combine the marks, then scale it back to the original range. We all do it, right? All of us do it as teachers. That's exactly what you can do with images. Okay, the concept is as simple as that. Okay, this is an image of the Powai Lake, or a couple of images here, and I'll show you an example of the mosaic, of the final mosaic image as well. Yeah, it's this. As you can see, this is this. इसमें थोड़े distortions तो हैं, right? This is right behind IIT Bombay. थोड़े distortions हैं, but apparently the mixing and all has been done rather well. So here, for instance, this is the student activity center at IIT Bombay. I was there at IIT Bombay for about 6 years and took a lot of pictures around. तो उसमें ऐसे लग रहा है कि जैसे कर्फ्यू लगा हुआ है यहाँ पे. Okay, it's not that bad. So what we did here was also something interesting. There were actually people moving about. So what we did was we tried to estimate the motion of these moving objects, remove these moving objects from the images and then mosaic them together. Yeah, this is inside one particular lab in IIT Delhi. This was about mosaics. Would you like to know a bit of theory about mosaics, a bit of the homography and such things? Okay, let's do it in a rather, pardon? Yeah, yeah. I was just trying to avoid the temptation of going to the blackboard for a long time. I guess I'll succumb to it now. Okay, let's suppose we consider two-dimensional transformations. Okay, so let's take. So please bear with my horrible handwriting. So, essentially the input is a 2D point and the output would also be a 2D point. Okay. So, one part of the board I will leave for drawing an overall diagram, and let us see what one can do with a point. First, let us start off with what is called a Euclidean or a rigid body transform. How does one characterize it? If you like linear algebra, then you would like to characterize it as follows. You can say that P dash is equal to R P plus T, wherein we will do a quick sanity check. This is a 2 cross 1 vector, this is a 2 cross 2 matrix, this is a 2 cross 1 vector, this is a 2 cross 1 vector once again. Does this sound familiar? This is a rigid body transform. All of us know what this is. अगर इसको matrix notation में लिखें, all that we are saying is if I have a point x y, if my original point is x y, right, I can multiply that by a rotation matrix. Rotation matrix तो हम सबको मालूम है, cos theta, maybe a minus sin theta, cos theta. कई जगहों पे ये साइन इंटरचेंज हो जाता है, right? That depends on our sign convention, clockwise या anti clockwise, what one takes as positive, what one takes as negative, that is immaterial. And plus let us say Tx and Ty. Does everybody understand this equation? If one doesn't like linear algebra, it makes sense to write it out. X dash is x cos theta minus y sin theta plus Tx, and similarly one writes out another equation. कितने parameters हुए इसमें? 3 parameters हैं transform के, theta, Tx, Ty. This is any general 2 cross 1 vector, and any arbitrary 2 cross 1 vector represents a translation. This represents a rotation. Why? Why does this represent a rotation? What are some nice properties of a rotation matrix? It is orthonormal. So, R transpose R is the same as R transpose is the same as an identity matrix, and plus this has some other interesting properties as well, like the determinant of R is always 1, like sin square theta plus cos square theta, that is always 1. This is a Euclidean transform. Alright, this is something that we are all familiar with. Alright, essentially we have one coordinate system here, you can rotate it or translate it to get another. Photocopying वाले problem में यही आता है. What you are doing with those A4 sheets is essentially you are, in order to align them, you are translating those sheets with respect to each other and you are also rotating them for alignment. So, that is a Euclidean transform. Clear? So, or in other words, I can write this problem as, of all transforms, is how badly can I deform a square. This is the problem that, this is the question that we will ask. We still want to have a family of linear transforms, मतलब lines will remain lines, उनको bend नहीं करेंगे. उसके होते हुए how bad can we get? So, if I apply, just remember this, alright, all of this math can be characterized by one statement, how badly can I deform a square. So, if I have a square, my drawing is pretty bad, and if I apply a Euclidean transform to it, at worst क्या कर सकते हैं, इसको shift कर सकते हैं इधर उधर या rotate कर सकते हैं. So, one will get a shifted and rotated square, that is it, nothing more, nothing less. Alright. This is a Euclidean transform. So, this is our basic starting point. In our hierarchy of transforms, we will put Euclidean here at the base level, alright, and also write a summary wherein I can say that P dash is R P plus T. right? Now we want to be more general. इसमें कुछ और डालेंगे. We will add scaling. ठीक है? If we add scaling, we get what is known as the family of similarity transforms. Similarity transforms में क्या है? I won't erase this part. This part I'll try to just build up. So see, I'm trying to get more general. अच्छा, सिमिलैरिटी ट्रांसफॉर्म्स को किस टाइप से लिख सकते हैं? आई कैन राइट इट एज फॉलोज. पी डैश, आई कैन राइट इट, ये तो पुराना जाना पहचाना यूक्लिडियन ट्रांसफॉर्म है. एडिशनली आई कैन पुट सम स्केलिंग. दिस इज अ स्केलर, दिस इज स्केलिंग इट. अब आप ये पूछ सकते हैं कि रोटेशन को ही स्केल क्यों किया है, ट्रांसलेशन को क्यों नहीं स्केल किया है? क्यों? एनी आंसर? Why did I not scale the translation? It's simple. If I scale a translate, pardon? हाँ, वो तो ठीक है. तो ट्रांसलेशन को क्यों नहीं स्केल किया? कहना चाहते हैं कि स्केलिंग डालें तो क्या होगा? Yeah, precisely. That's exactly the answer. If I scale a translation, it's just another translation, right? It doesn't change the nature of what's trying to happen. On the other hand, this changes the nature. Okay, so this I can write in terms of matrix notation as x dash y dash should be equal to some c into our familiar sin theta cos theta matrix plus some constant translation. अब इसको लेट्स कॉल बाय सम अदर नेम. ठीक है, लेट्स कॉल दिस b. So if I have p dash, I can write this as b p plus t. This is a similarity transform. This is a bit more general because now we have scaled rotations. All right, इसमें यही होगा कि still metric properties would be preserved. All right, because the relative, this would be rotated, translated and scaled version, right? So if I have a square, इसको at worst I can translate it, rotate it, scale it. We can't do anything more to it. All right, थोड़ा general हुआ, but metric properties like relative distances, relative angles are still preserved.